Hello, welcome to Chapter 5, Section 5. The title of this section is Complex Numbers and Roots, Complex Roots. So, in the previous sections, we've been talking about how to solve quadratic equations and how to find zeros of quadratic functions. And we've learned a couple of different ways. So we learned how to do it by graphing. We learned how to do it by factoring. Sometimes factoring doesn't work. So we learned how to do it by using square roots. And if the square root is not a direct course, then we can make it work by completing the square. But now we're running into a problem. What if I have this type of situation? What if I have an equation that looks like this? X squared plus 1 equals 0. That's a quadratic equation. It has x to the second power. And one of the things that you've heard me say over and over again is that there are always two solutions to this equation, or roots of the equation. We also talked about the fact that there's always two zeros if I graph it. All right, well, let's see if I can solve this. This doesn't have a middle b term, so I don't need to complete the square. I take x squared plus 1, and I'm going to add negative 1 or subtract 1 to both sides, and I get x to the second power equals negative 1. Let's keep doing what we did in the last section, and I'm going to take the square root, and I'm going to get 1 positive, 1 negative. Okay, there's my two roots, but here's my problem. What does the square root of negative 1 mean? And why is that difficult? So let's do it with something that we know. Let's say if I was doing the square root of 25. And again, if I put a plus or minus in front of it, that tells me the two roots of the equation. I'm just talking about the principal square root of 25. So the square root of 25 equals 5, because 5 to the second power equals 25. These two are inverses of each other, so they go hand in hand. But if I did solve this as a quadratic equation, and I had x to the second power equals 25, not only am I dealing with the principal root, but I'm also dealing with negative. So my two choices would be x equals 5 or x equals negative 5. Now think about this. 5 to the second power equals 25. That means I'm multiplying 5 times itself. 5 times 5 equals 25. Negative 5 to the second power, and I have to put it in parentheses because of the way I have to write algebra. This means negative 5 times negative 5, and that also equals 25. And what got lost in all this is that this is a positive number times a positive number, and this, actually right there, is a negative number times a negative number. Well, what happens if I have a positive times a negative? I get a negative. And if I have a negative times positive, the commutative property still gives me a negative. But those are not the same. So 5 times negative 5 equals negative 25, but these are not the same. Why is that important? Because if I found the square root of negative 25, I need to find what number multiplied by itself equals negative 25. Well, if it's a negative, negative times negative gives me a positive. And if it's positive, positive times positive gives me a positive. So all of the problems that we've done so far, let me clean that up a little bit. All of the problems that we've done so far have had only positive numbers under the radical. Now check this out. If I do this on the calculator, so I'm going to do square root, put negative 25 in my calculator, calculator says, nope, not going to do it. That's an error. The calculator does not understand how to do this. So we are going to make you smarter than a calculator. I want to go back to this one for a moment. What if we were to do this? I guess I didn't need to move the paper, sorry. What if I was going to do this by graphing? And I said f of x equals x squared plus 1. That graph is going to look like this. It's the parent function x squared with a vertical translation up 1. So instead of my origin, instead of my vertex being at the origin, my vertex is now at 0, 1. Where does this graph cross the x-axis? There are no zeros. Or actually, are there? So this is where we bring into the idea of an imaginary number. And I do not like that we call that imaginary. There is a mathematician named Gauss. Hopefully I'm spelling his name correct. And his idea was to actually call these lateral numbers. And I am going to post the link to a really cool video that's going to explain this. He calls them lateral numbers because, and I'm kind of running out of space here on, on my stuff. Do I have like a blank sheet of paper here? He calls them lateral numbers because if you think about our traditional number line, so we have 0, here's 1, 2, 3. We also have negative numbers, -1, -2, -3. We have fractions, so 2/3 is right here. We also have irrational numbers. Pi is about right there. The square root of 2 is about right here. And if we went over this way, make sure I'm getting in the right place. This would be negative square root of 2, so that would also be irrational. So all the numbers that we know are on here. So Gauss, and the video explains this way better, and I'm going to explain this. Gauss says, well, then we can actually talk about lateral numbers being off the side. So then going this direction, we would have imaginary numbers. And we call these lateral numbers because they're off to the side of what we call real numbers. I don't like the word imaginary because it makes it seem, I kind of reckon it like if I was a biology teacher, I would never feel comfortable saying, okay, we've been talking about single-celled animals, we've been talking about plants, we've been talking about invertebrates, we've been talking about vertebrate animals, animals that are vertebrates. Now we're going to talk about imaginary animals. It's like, what are we talking about? Like, you know, unicorns and, well, sorry, I don't want to list anything because if you believe in unicorns, I apologize for that. So as soon as I start saying imaginary numbers, it makes me feel like I'm talking about something that we don't need to deal with. But actually, imaginary numbers, if we call them lateral numbers, is just a different type of number. And it would be great for us to ignore this and just say no solution. So we could actually get to this point right here and say no solution, which is what we've done so far. But the thing is that we actually need to have a solution for that. Why do we need it? Because quadratics is not where we're going to end. We're actually going to start talking about equations that have x to the third power, x to the fourth power, x to the fifth power. And when we solve those equations, we're going to end up with a need for these type of numbers. Okay, so that's the reason behind all this. And like I said, there's other ways of explaining this that are a little bit better. And again, I keep thinking about that, the video. I'll post the link in Schoology, so please watch that. There's a lot of information in there that might be a little bit advanced, but I think if you watch it, you'll get a good feeling for why this is important. So how do we actually handle this? All right, I'm going to go back to this piece of paper. Just need some blank paper. You can see it's been there the whole time. So what we do is we make a definition. And remember, algebra is a language. So just like we define words in English or Spanish or Hmong or whatever language we're speaking, we can, and those words have ideas. Okay, so like in English, if I said dog, that's actually an idea. It's a type of animal. So then I can make a connection between the idea of what a dog is and the actual sound we make when we say dog and the symbols that we use for that. Okay, so this is a connection between a symbol, a picture, and what the idea is. So when I get stuck and I have square root of -1, I don't know what that is. So I define it and I call it I. Now, congratulations, because there are 5 of the most important numbers that are going to exist. All right? This is the 4th one. You'll meet the last one in chapter 7. What numbers am I talking about? The number 1, which is the multiplicative identity, the number 0, which is the additive identity, pi, which is the ratio of the circumference over the diameter of a circle, and now we have another number, which is I. The last one I'll talk about when we get to chapter 7. So, whenever I see the square root of -1, I'm going to change that to I. So let me do a couple of problems for you real quick. We're just going to express these radicals in terms of I. And this is how it works. This is 3. -16 is -1 times 16, so it's the square root of -1 times the square root of 16. I know what the square root of 16 is. It's 4. 3 times 4 equals 12. The square root of -1 we just defined as I, so I just write 12i. That's it, 12i. Let me do this one instead of that one. Well, I guess it doesn't matter. That one's got the negative in front of it, so I'll talk about that. But let's do this one, all right? This is the square root of -1 times the square root of 4 times the square root of 3. If you don't know why I did square root of 4 times square root of 3, go back and watch the videos for section 1, chapter 1, section 3, 1-3. I'm simplifying this. But -1 times 4 times 3 is -12. Square root of 4 is 2. Square root of -1 is I, and the square root of 3 is just the square root of 3. Now you're probably wondering why I rearranged it. Usually we put the constant or the coefficient in front. Then we put the I, and then we put the radical, if there's any radical, after. Last time there was no radical, so it was just 12i, right? If this one was just 2i, I would have just left it like that. The reason why we put the radical last, most of the reason is because it's open on the right side, so sometimes it gets a little confusing. If I wrote, I'll go back to this one. If I wrote square root of 3i, see how sloppy I was? Is the I under the radical or outside of the radical? So that gets a little confusing. All right, let's try this one. I got a negative here, that's -1. -75 under the radical, that's going to be the square root of -1 times the square root of 25 times the square root of 3. How did I know 75 was the square root of 25 times, 75 is 25 times 3? Because I'm going to factor 75 into the biggest perfect square. And the biggest perfect square that is a factor is 25. Now, this is -1. This is I. This is 5. And that's square root of 3. The square root of 3 is going to go last. -1 times 5 is -5. That's I. So I write -5i times square root of 3. This one, I guess number 4. 2. Now I'm going to do my radicals. -36 is -1. And 36 is a perfect square. So I know what that is. square root of 36 is 6. 2 times 6 is 12. And the square root of negative 1 is I. So basically, it's the simplifying that we know already with the things under the radical. The numbers under the radical are negative, so you just make sure you include the I with it. That's all there is to that. Now, before I go and finish up this video, I want to talk about something that is very important. And again, I'm just got a blank sheet of paper here, or the paper I was writing on. We know that the square root of negative 1, we call that I. So, if we start with, and I'm just going to turn this around, we say I, that means the square root of negative 1. So what is I to the second power? What's I times I? Well, if I take the square root of negative 1 and I square it, that just equals negative 1. And of course, that's where I get into the idea of squaring something and getting a negative. Okay, well, let's keep up this pattern. Let's see what happens. What is I to the third power? All right, so that would be the square root of negative 1 times the square root of negative 1 times the square root of negative 1. These two multiplied is what I had up here, negative 1. This is I. Negative 1 times I is negative I. Now this is going to be really cool. What's I to the fourth power? Well, let's think about it. If I have square root of negative 1 times square root of negative 1 times square root of negative 1 times square root of negative 1, multiply these two together, I get negative 1. Multiply these two together, I get negative 1. And if I multiply these two together, negative 1 times negative 1 equals positive 1. Okay, that's all good. What's I to the fifth power? Okay, now this is the cool part. I to the fifth power is going to be, and I'm run out of space here, sorry, but I to the fifth power is going to be I times I to the fourth power. I to the fourth power is 1. So that's just 1 times I, which equals I. And what happens is I start the whole thing over again. And I'm out of space. But I to the eighth power goes back to positive 1. We'll say more about that when we get to complex conjugates.